Hello and welcome back to my channel. In this video, we'll be looking at a second example for the greedy algorithm. In the last video, we looked at our first example, and in this video, we'll be looking at the second. And we won't just solve the problem, we will also write a proof of correctness by induction for this problem. Let us consider a long, quiet country road with houses scattered very sparsely along it. We can picture the road as a long line segment with an eastern endpoint and a western endpoint. Further, let's suppose that despite the bucolic setting, the residents of all these houses are avid cell phone users. So you want to place cell phone base stations at certain points along the road so that every house is within 4 miles of one of the base stations. So the question now is to give an efficient algorithm that achieves this goal using as few base stations as possible. So this means that our objective is to minimize the number of phone base stations we install along this road while maximizing the neighborhood's reach, or maximizing their use. So we want them to derive maximum satisfaction while also minimizing the number of phone bases. So how do we solve this problem? If you may, pause this video for a minute or so, think about it. How would you solve this question? And when you're done, just let's get back and talk about it together. So for this question, let's start with the inputs. What are your inputs? So I would say we have n phone base stations to be placed along the road, right? And we want every house along the road to be within 4 miles of a phone base station. It's stated here. We want every house along the road to be 4 miles from each phone base station, right? Yeah. Okay. So what would our strategy be? What do you think? So I would say for the strategy, we are going to start from one end of the road. Let's say the west side. Remember that the question said we can imagine the road to be a line running from west to east. So for our strategy, I want to start from one end of the road. Let's say we are starting from the west end and we are going to be moving towards the east. Now, I'm going to sort the houses along this road, starting from this west end according to their positions. So we want H. Let's say that H denotes the first house at the west end. Then if this is the first house at the west end, let's call this H, right? I'm going to place my first phone base station exactly 4 miles from this first house, which is H. So at H plus 4, let's say this is H plus 4, right? Which is 4 miles to the right of H. I'm going to place my first phone base station. So this is my first station at this point. So Now, this phone base station is 4 miles from H and also 4 miles from all the houses after H plus 4, right? This is 4 miles. This is 4 miles. So I'm going to remove all of these houses, everything here. I'm going to remove them. Then I'm going to repeat the same process. And I'll repeat this process until I cover all houses up till the last house here. So to repeat this, just like we did for the first one, let's say this is H plus 8 here. So I'm going to count 4 miles from here, which is H plus 12. So this is where I'm going to have my second station, right? And this second station covers houses from this and houses to this, which is at H plus 16. So I'm going to remove everything here and then repeat the process. So this is what my strategy is going to be. This is the strategy I would use if I were to solve this problem. So what are my observations? Let's think. Using this strategy, what do you observe? I think this strategy implies that for every 8 miles, that's the first 4 miles and the next 4 miles. So for every 8 miles, we will have one phone base station placed at its midpoint. This is an illustration already, just as I've illustrated. For every 8 miles, I have one phone base station in the middle. I hope this makes sense. So let's write our proof of correctness. Our proof of correctness by induction. So as usual, before you start writing the proof, what do you want to prove? We want to prove that our greedy algorithm stays ahead. And in this case, if our greedy algorithm stays ahead, it means that we are using fewer base stations. The greedy algorithm is using fewer base stations. So before you start to write any proof, please think about what you're actually proving. So as usual, we want to prove that greedy stays ahead. And what does that mean for this instance? Greedy stays ahead, and it implies that greedy uses the fewest number of base stations possible. Uses the fewest number of base stations. So next, let's move on to our definitions. So the next thing we do after figuring out what we are proving is to move to the definitions. So the first one, I usually use A subscript I for the greedy. So A subscript I, let's call this the position of the last house covered by the first I base stations in greedy solution. The position of the last house covered by the first I base stations in the greedy solution. So this means that OPTI would also be the position of the last house covered by the first I base stations in the optimal solution. Okay. So now let's define our measure of goodness. How are we going to define our measure of goodness? What do you think it should be? Okay, so let's say that our measure of goodness is the position of the last house the position of the last house covered by the first I base stations in solution. The position of the last house covered by the first I base stations in solution. So I need you to stop and think about this measure of goodness. There are many different ways to define your measure of goodness. But supposing we are using this as a definition of a measure of goodness, what does it mean? We said measure of goodness is the position of the last house covered by the first I base stations in solution. So it means that our claim now, for our greedy, the position of the last house covered by the first I base stations would be farther. That means our greedy would cover more houses, right? By let's say this I is 2. So if we have 2 base stations, our greedy will cover more houses, right, than any other solution. So it means that our claim would be that this is greater than or equals this. I hope this makes sense for all I. So I hope this makes a lot of sense to you. I hope this makes a lot of sense to you. Let's look at this illustration again. With our greedy, right? With only 2 base stations, we've covered from H to H plus 16. We could have used another algorithm. Let's say the algorithm is that we plant a station after every 4 miles. But if we do that, 2 stations would only cover from H to H plus 8, right? So we see that the greedy covers more distance. The position of the last house covered by the greedy for a given I base stations would be more or will be further than that's covered by any other solution. I hope this makes sense. Okay. Let's also suppose that we have a different definition for our measure of goodness. Let's say that our measure of goodness is the number of base stations. So if we define our measure of goodness as the number of base stations, it means that our claim now would be that the greedy would use lesser number of base stations compared to the OPTI. So this would be our claim. I need you to understand that your claim depends on your measure of goodness. That's one thing I need you. If you don't take anything away from this proof, please let it make sense to you that our claim, whatever our claim is, depends on what you define your measure of goodness to be. Okay. So the claim that the position of the last house covered by the greedy algorithm is further or equal to the position of the last house covered by the optimal solution implies that the number of phone bases needed to cover up till the last house will be less than or equal to the number of phone base stations needed to cover up to the last house in the optimal solution. So yeah, if we say that the position of the last house covered by the greedy is further than this, so I think I will just illustrate again. Let's say this is H plus 4, H plus 8, H plus 12, H plus 16. So let's say from our algorithm, we had a first station here, second station here, right? So if the position of the last house covered by these 2 stations is this is the position of the last house. So it implies that the number of base stations we need to cover this whole distance for the greedy will be less than, right, the number of base stations we will need to cover this same distance. Supposing we used another algorithm that that covered less distance for this same number of base stations. Let me say that again. The number of base stations that covered from H to H plus 16 is 2 for the greedy. And this gave us the farthest position for the last house. Yeah. Now, for the optimal, let's think about another algorithm. Let's call it an optimal solution that uses these same two base stations, but then it covers only here and here. So for this optimal, we have a shorter position. It just covers from here to here. So that means if we want this optimal, right, to cover up to this point that greedy has covered, the optimal is going to use more base stations. So here you have 2 base stations for this same position or for this same distance, but optimal will use 4 base stations. I hope this makes sense. Okay, so I haven't illustrated this. Let's 2 base stations. I hope this is clear. Having illustrated this, let's move to the base case. So our base case where I is equals 1. So when we have only one house, optimal, let's say we have just house 1, our optimal would use 1 base. Let's call that 1 base station. And our greedy would also use for house 1. Our greedy would also use 1 base station. And our claim for all I is still correct based on this base case. So our claim holds. So let's look at the induction. By induction, let's assume again, as usual, we assume that mi minus 1 is greater than mopti minus 1. So if that's the case, for a given I base stations, the greedy would cover more houses or distances than the optimal, and this implies that the greedy uses fewer base stations than the optimal solution for the same length for the same length of road. The illustration for this is same as I've given here already. That's the illustration. So we can see that from the illustration we gave, for a given number of phone bases, the distance covered by greedy is more, just like I said in this illustration. If we were to use only 2 phone bases, this and this, for the greedy covers more than any other algorithm. If this uses only 2 bases, only 2 phone bases, it stops here, but greedy stops at H plus 16. So greedy covers more distance or more houses, as you may say. But for the same number of houses or the same distance, we see that greedy uses fewer phone base stations. The optimal will use more phone base stations. So we say that the greedy algorithm in this solution minimizes the phone base station used to solve this problem compared to the optimal solution. The number of phone stations used in the greedy algorithm is less than or equal to the number of phone base stations used in the optimal solution. So we see that our claim also holds here. Claim also holds in this case. So I hope you had fun while thinking about this question. If you did enjoy this video, please subscribe, hit the like button, share with your friends, comment. I would like to see your comments, and let's meet on the next video. Thank you.